Hi, welcome to part 2 of ECE 141 Lecture 10 on Information Theory, an introduction to Information Theory. We left the previous lecture talking about source coding. Let's formalize it. Source coding, well, let's have these assumptions first. Data is noiseless, there won't be any corruption due to noise. Your source alphabet has finite number of elements, basically how we define the data source from the previous lecture. And the statistics of the source is known. Basically, we know the a priori probabilities of the symbols that are being sent by the data source. So the goal of source coding is basically to be able to represent the data from the source completely without any loss, right? And optimally represent it in such a way that we want to minimize the number of bits that will be used to represent the information. Okay? So basically, we don't want any data lost when representing the information. The intuition here is that, okay, maybe we should reduce the number of bits on different symbols and retain the number of bits on other symbols. With that, we define the average code word length, basically the number of bits per symbol that you use to represent the information coming out of the data source. The average code word length is basically the expected number of bits that will be used to transmit or represent the data. Okay, so it's defined by this equation as you see right here. Okay, so uh, this is the number of bits, expected number of bits per symbol that you will use to represent the data. So now we define the coding efficiency as eta will be the minimum number of bits, the most optimal code word length divided by the one that you used. So how do we determine the minimum or the optimal code word length? What is the theoretical minimum? So say assume a stream of information represented by vector x taken from the symbol set a1 to an. So this is a finite set with cardinality large N or capital N. Let's say the vector x has a very large length n, and let the source be memoryless. So that would mean that your uh, vector x would be a typical transmission because of the large n. Since it's memoryless, it's a typical transmission. Basically, it's the most probable stream of symbols that will be measured or will be observed from the output of your data source. Okay, so a vector x is equal to a series of information or a series of symbols from your source. And if we want to, if we have your symbol a sub I, with a probability of occurring p sub I, if you want to get the number of a sub I that occurred in vector x, it's approximately equal to n, the number or the number of symbols that were transmitted, multiplied to the probability that a sub I occurred. This is the most probable number of a sub I. So since n is very large, we can say that this approximation is accurate due to the weak law of large numbers. So if you want to know more, you can search that. So the probability that the transmission is the vector x becomes this. So basically, all of the symbols will be the probability of that happening is basically your symbol p sub I, the probability of your symbol p sub I raised to the number of times it occurred. So p sub I raised to n p sub I. So if you take the logarithm of the probability, which is equal to the logarithm of this, your pi multiplier or your pi operation will become a sigma operation or summation, and your terms inside your pi operator will become this expression right here. And since n is constant with respect to the operator, we can factor that out. This sum of pi log pi is equal to negative of the entropy of the source. So the the logarithm of the probability of your stream x is equal to this. So now, since x is a typical sequence from a set of all typical sequences A, and n is very large, so with n very large, the entropy of capital X, which is a vector, which is a random variable taken from the set of all typical sequences. So your random variable is actually at maximum, which occurs at the second logarithm of C of A. So according to the law of large numbers, since n is very large, your random variable will have a maximized entropy, and that is equal to nh of x, which is what you got here, okay, which should be equal to logarithm of the cardinality of set A. So the cardinality of set A, since it's maximized, is equiprobable, so it's 1 over the probability of x, small x occurring, which is equal to 2 raised to nh of x. So this is from this equation right here. So basically, the number of elements of set A is equal to 2 raised to nh of x. In terms of the number of bits that we use to represent the information from set A, that is equal to nh of x. Basically, we need nh of x bits to represent uh, the sequence from set A. So the stream of information with length n can be represented with nh of x bits. If we get the number of bits per symbol, we just divide this nh of x by n. Then per symbol, we need h of x bits per symbol, okay, at the minimum, to represent the information coming out of a data source x. And this is Shannon's first theorem, or the lossless source coding theorem. Let's formalize that. Shannon's first theorem let x denote a discrete memoryless source with entropy h of x. There exists a lossless source code for the source at any rate L bar if this L bar is greater than, oops, sorry, there should be greater than or equal to h of x. Okay, if you go if you use less than what is the entropy, then you cannot, or you won't be able to represent your information properly. Okay, or you can still represent the information, but it will become lossy and it will undergo lossy compression. Oops, sorry, not underline that properly. Let me just erase. So it becomes a lossy compression if you try to represent the data less than the entropy of the information source. L bar, sorry, should be L bar, which we defined earlier, is called the average code word length of your data source. All right. So if you want to optimize the data that is coming out of your information source, you need to use a less amount of bits to represent it. Okay. The trade-off here is that if your coding is very efficient, you'll need to use a lot more hardware to be able uh, to represent or to be able to process it. There you go. So an example of that, so I urge you to explore this yourselves, is using video formats. The MP4 or MPEG-4 is an example of a lossy compression. Right? So if you try to compress your video data, it becomes more blurry, more pixelated because it's a lossy compression. You won't be able to represent the images more properly from your lossy compression of MP4. Right? Uh, there is a form of coding in videos that is HEVC, highly efficient video coding. So I discovered this when I was watching some series. Okay, uh, HEVC would compress a 1080p. Okay, so imagine this 1080p of a 1 hour uh, 1 hour episode, it can compress your 1080p video to 200 megabytes. So imagine uh, how much storage space you'll be able to save. Because normally, if you think of 1080p and 1 hour, it's around gigabytes, 2 gigabytes. I don't know, 1 gigabyte. If you use HEVC, highly efficient voltage, sorry, highly efficient video coding, it's talking about voltage, high efficient, highly efficient video coding, your 2 gigabyte file will become 200 megabytes. But if you try to open it and play it, your processor will take a lot of power to be able to stream it properly. Anyway, that's an example of a lossless compression. So, example. Let's say you want to represent your symbol set X, whose elements are 0 to 5, and assuming we have equiprobable symbols. The entropy of this set is 2.585 bits. Normally, when we don't have any knowledge about coding, we'll just think that okay, uh, we can use 3 bits to represent these 6 symbols. However, there are 2-bit combinations that will be unused. Okay, and the uh, the amount of bits you use to represent the data here is 3 bits per symbol. As you can see here, use 3 bits, 3, 3, 3, 3, 3. So we want to be more efficient. Let's reduce the number of bits. But if you do that, you won't be able to represent 2 of the data. So this results into a lossy compression, and you lost 2 symbols that you're not able to represent because you used a number of bits less than the entropy of the source, as you can see right here. Okay, so this is a consequence of trying to represent the data much less than the entropy of the data. Okay, now let's try something like this. Maybe the set from 0 to 3, we represent the first bit as 0 and then append 2 bits. I append 2 bits to represent the different data from 0 to 3. And then 4 and 5, the first bit is 1, different from the first 4, which is the first bit is 0. 4 and 5 has a bit 1, and you need one more bit to represent it if it's 4 or 5. Okay, so if we use this, the average code word length becomes 2.667 bits per symbol, which is closer to the entropy as compared to this representation, which is 3 bits per symbol. Or this, well, it's less than the entropy, so it's lossy. And basically, this is more efficient coding compared to what I presented to you earlier. So to be able to generate more efficient coding of data, we use what we call the Huffman algorithm, or Huffman coding. It's a type of variable length algorithm, sorry, coding algorithm. It has not 2 steps but 4, but mainly just 3 and 4 means just repeat step 1. Okay, so it's actually just 2 steps. The symbols you combine, or you get the 2 symbols with the lowest probabilities and assign a bit to them, 0 and 1. So it doesn't matter which of them is bit 1, which of them is bit 0. You add the probabilities of these 2 symbols and you get a super symbol. And then you go back to the drawing board and compare your new symbols, your super symbol compared to your other symbols that you have not used, and then you repeat the process until your probability, the total probability that you have added, is equal to 1. Basically, you've finished assigning bits to every symbol that you have in your tree, and then you read from the top of the tree to the bottom of the tree, and then you get the representation for your data. For example, let's go back to the set earlier, set X with 0 to 5, assuming equiprobable symbols. We start our tree at the bottom. We list down 0 to 5 right here. and each of their probabilities, which is 1 over 6, right here. So since all of them are equiprobable, we just combine the adjacent symbols with each other, like 4 and 5, assign 0 and 1, 2 and 3, assign 0 and 1, 0 and 1, assign 0 and 1, then add their probabilities. As you can see here, at the next level of the tree, the probabilities are now 1/3, 1/3, and 1/3. So it doesn't matter since they have the same probabilities. Doesn't matter which you choose, you'll still end up with the same average code word length. So let's choose the adjacent symbols right here. So 1/3 and 1/3, you combine them, assign a bit 0 and 1, doesn't matter. This could be 1, this could be 0, doesn't matter. So you add them, it becomes 2/3, and you combine it with what is left, 1/3 right here, and assign a bit to both of them. And you add them, you get total probability of 1, and then you have reached the top of the tree from here. Now to get the symbol or the bit assignments for each symbol, you have to work your way down the tree and get the bits as you go along. For example, in symbol 0, you start here, and symbol 0 would be 0, 0, 0. That's why it's 0, 0, 0 right here. Your symbol 1, 0, 0, 1 right here. Symbol 2, 0, 1, 0 right here. Symbol 3, 0, 1, 1. Symbol 4 is 1, 0. Symbol 5 is 1, 1. And this is the same that we had, the same thing that we had earlier from the previous example, but now we have formalized its algorithm to determine the representation. Alright, let's shake things up a little bit. Let's say the probability of the symbols occurring are different from each other. Right. So this is the set of probabilities for this set of symbols. Okay. So now you see this different tree that we had earlier. So how did this happen? First, in the first level of the tree, get the two symbols with the lowest probabilities. So that's 4 and 5. 4 and 5 has the lowest probabilities. Assign 0 and 1 to both of them. Okay. Now add their probabilities. You get 0.18. What is left here is 0.18, 0.12, 0.15, 0.25, and zero point 0.3. As you can see from this set, okay, the lowest probabilities are 0.12 and 0.15. So you combine them together, you get 0.37, and then you assign bits to the symbols that you combine 0, 1. Now you're left with the set 0.3, 0.25, 0.27, and 0.18. You get again the two symbols with the lowest probabilities. That's this 0.25 and 0.18. Combine them together, assign a bit. So 1 would be 0, and then this level of the tree right here is 1. Combine them, you get 0.43. You're left with this, and this. So 0.3 and 0.27 would be the two lowest probabilities. Combine them, assign a bit, 0 and 1, add them, 0.57. Now, you're only left with two symbols, 0.57 and 0.43. Combine them, add them, you get to the top of your tree and assign the bits 0 and 1. Doesn't matter. This could be 1, this could be 0. Doesn't matter. So let's arbitrarily assign 0 at the top and 1 at the bottom. So now you're done with your Huffman coding tree, and then you get the representation. So your bit 0 is 0, 0 here. Your bit 1 is 1, 0 here. Your symbol 2 right here, 0, 1, 0. Symbol 3 is 0, 1, 1. Symbol 4 is 1, 1, 0. Symbol 5 is 1, 1, 1. So if you get the entropy of this random variable x, you get 2.422 bits per symbol. And your average code word length, if you use Huffman coding, is 2.45 bits per symbol, which results into a coding efficiency of 99%. So that's how efficient the Huffman coding is. Right. So it'll give you some time to absorb this altogether. Right? So just some notes. Symbols that have more probability of occurring has less number of bits used to represent them. Right? So that's a general rule when you're designing an efficient source coding. Okay, just so some notes on Huffman coding. The average code word length is bounded by these two, your entropy and entropy plus 1. In the previous examples, also, no code word is a prefix of another code word sequence. So as you can see, if we get the first bit as bit 0, it's either 0, 2, or 3. If the first bit is 1, it's either 1, 4, or 5. So basically, we are able to instantaneously decode the bits that we will get. Okay, as you can see, this 0, 0 cannot be found in the first two bits of the others. This 1, 0 pattern that cannot be found in the first two bits of the next two. Okay. So decreasing r below h of x, again, would produce losses or produce errors, because this means that your source is uh, trying to convey less information that actually does. So how do we increase the efficiency of Huffman coding more? Maybe if we combine your uh, symbol output of your data x into uh, one super symbol. Let's say you take n of those, create one super symbol, and use the Huffman code to represent your new set of symbols. The average number of bits will go down, okay? And the new bounds of your coding will become bounded by, again, of course, the entropy of your source and the entropy plus 1 over n. If n approaches infinity, your coding rate will be squeezed by h of x and h of x, which will make your code rate be equal to the theoretical minimum. Okay? And this is referred to as the nth extension of the Huffman code. For example, let's say we have a binary source for simplicity. It's a very biased source with A1 occurring 9 out of 10 times and A2 occurring 1 out of 10 times. The theoretical minimum is the entropy of the source, which is around 0.47. If you pair them up, so you get a set of two symbols, could be both of them could be A1. The first could be A1 and the second is A2. The first could be A2 and the second is A1, and both could be A A2. All right. So if A1, two A1s occurring is 0.01, sorry, 0.81, that's zero point 0.9 times zero point 0.9. A1 then A2 occurring is 0.09, and A2 then A1 occurring 0.09. Both A2 occurring is 0.01. And then, excuse me, we use the Huffman coding to represent their bits. All right. So 0.01 right here and 0.09 are the lowest probabilities. So combine them, you get 0.1, assign your bits. Lowest probabilities, 0.1 and 0.09, combine, assign bits. And 0.19 and 0.81, combine, you get 1. You get to the top of your tree, assign the bits. And then work your way down to get the representation. If you get two A1s, you represent them collectively as 1, 0. If you get A1 and A2, you represent it as 1, 0. A2 and A1, 1, 1, 0. A2, A2 is 1, 1, 1. And if you get the number of bits per symbol, as you can see here, you will get 0.645 bits per symbol, which is closer to the theoretical minimum compared to the binary source. If you only use a single symbol, inevitably the code word length, the average code word length will become 1. But if you pair them up, you can decrease your number of bits per symbol, your average code word length, and increase the efficiency of your coding. And this is actually what is used for different coding schemes in computers. Another widely used coding aside from Huffman is the LZ algorithm. So the LZ algorithm is used to compress zip files. So if you're interested, I suggest you read up more on that. But for this course, we'll only discuss the Huffman coding. Hi. Now, let's look at the case when we transmit our data through a channel. So now, noise comes in. So your symbol Y is a noise corrupted version of the transmitted symbol X. If you have a stream of symbol inputs, vector x, you will have a stream of symbol outputs, vector y. The channel is memoryless if this equation holds. What does this mean? It just means that your output y sub I is only dependent on the input x sub I and nothing else. That would mean that the channel is not an LTI filter, or you have already equalized the channel properly. So review your equalization from the previous lectures, lecture 9, and let's move on to an example. For example, your binary symmetric channel. The set of inputs and outputs only come from the set of 0, 1. Let the probability of error be, let's say it's P, right here. So the probability of correct decision is 1 minus P, and the probability of error, as you can see, is P. That means from 0, it will become 0 with the probability 1 minus P at the output. From 1, it will become 1 at the output with the probability 1 minus P. So from 0 to 1 and 1 to 0, the probability here is P, as you can see in this figure right here. Okay. Okay, so I apologize for the pause. So transition probability matrix is basically defined as the matrix of the transition from one bit to another or one symbol to another in your channel. So basically, the first element here, P11, describes the probability that Y1 is received given that X1 is transmitted. P12 is the probability that Y1 is received given X2 is transmitted, and so on and so forth. This matrix right here describes the behavior of the channel. And from this, you can actually get the channel capacity. The channel capacity is defined as the maximum information I of xy, mutual information I of xy, give the maximum mutual information I of xy depending on the probability distribution of x right here. So this is the channel capacity measured in bits per symbol. Basically, what is the maximum amount of information you can transfer by observing, or you can infer by observing y, okay, and trying to determine x. Okay, so this is your maximum channel capacity. And the maximum bit rate the channel can carry is if you just multiply the channel capacity by the, the symbol rate right here. So you multiply bits per symbol with the symbol per second, you get bits per second. So this is how you will derive the capacity of the channel. So example, the additive white Gaussian noise. The output of y here is continuous and the input x is discrete. So we have a digital communication system operating in an analog world. The uh, mutual information between x and y is defined as this. The entropy of y can be taken from a Gaussian distribution. Since it's a Gaussian distribution, you'll be able to get h of y right here. The next step is to get the conditional entropy of y given given x. So that is equal to this equation right here. So this a posteriori probability is equal to this equation right here. You integrate that, you integrate the whole of this. The Gaussian distribution h of y given x is equal to this expression right here, where n naught is the noise variance. Or sorry, n naught here is the power spectral density magnitude of your additive white Gaussian noise. So the channel capacity now becomes what probability of x will maximize, or what will maximize this expression inside right here. This will be maximized if h of y is maximized. Won't matter here, it's just noise. H of y here will be maximized if it is again Gaussian. So we want to maximize h of y if it's Gaussian, then its entropy is equal to this 0.5 log of this expression inside, where sigma y is the variance of the Gaussian random variable y. And note that this variance right here is directly related to the power of the signal y, which is equal to the power of signal x plus the power of the noise. Right, so substituting that at the original equation, your C prime will become this, and getting or substituting sigma y to this expression, you'll get this equation inside your C prime, your channel capacity, and it's basically 0.5 logarithm of 1 plus your signal power divided by your noise power. This is the channel capacity of a noisy channel. Okay. So now, let's move on to Shannon's second theorem. You will be able to achieve reliable communication over a discrete memoryless channel if your data rate is less than or equal to your channel capacity. So let's put again an equal right here. Okay. So reliable communication is possible if your data rate is less than or equal to your channel capacity. At rates higher than the channel capacity, you won't be able to get reliable communication. Okay. So let me try to demonstrate that for you. You want to get reliable communication, you need to have a rate greater than the channel capacity. Did you understand any word I said? I try to speak as fast as I can without stuttering, but the words become unintelligible. So if I try to slow it down, it becomes easier to understand, isn't it? Okay, this is Shannon's second theorem. So another analogy is when you're trying to transfer water from a well to your house, okay, bring it home, you are limited by your strength, the size of your pail, and some external factors when you're transferring your pail to your home. Okay? So that is where the formula of the band-limited Gaussian channel comes from. So C prime is equal to this. If we multiply this by the data rate, RC, which is mainly twice of your bandwidth BC, so the channel capacity is equal to this equation right here. And this is the Shannon-Hartley capacity theorem. Just some note, uh, this equation right here is true for ideal conditions. That means your symbol rate is twice the bandwidth. That is when you have an ideal, your frequency domain is of your pulse is ideally a square or rectangular pulse in your frequency domain. So we already proved that this is impossible from lecture 9, but okay, let's say it is possible here in theory. So your theoretical capacity is equal to this. And this is called the Shannon-Hartley capacity theorem. From here, you can actually derive the Shannon limit. So say you get your signal power, which is basically the energy per bit multiplied by your bit rate. And the noise power is equal to the power spectral density of the noise multiplied by the bandwidth. Of course, since you're band limiting the channel, your noise power also reduces. Shannon-Hartley capacity is equal now to this equation right here. So if we get the capacity per bandwidth right here, we get this expression inside. Okay. So now we can get a relationship of your signal to noise ratio and your spectral efficiency. So this is SNR, okay, SNR per bit. This is your spectral efficiency eta. So you will see actually that when you try to relate them, if you want to uh, reduce your efficiency right here, if efficiency is reduced, that means your bandwidth becomes infinity, okay, at constant data rate, uh, EB over N naught will be limited to negative 1.6 decibels. Okay. It will asymptotically approach negative 1.6 decibels. What does that mean? It means that if your SNR per bit becomes less than that, you won't be able to achieve reliable communication. So we call this negative 1.6 decibels right here as the Shannon limit. Okay, any SNR lower than that, negative 1.6 dB, at infinite bandwidth, we cannot guarantee a reliable communication. So remember the case when we had an infinite bandwidth, right? What would be the SNR needed to get a good bit rate? So that is your recall your FSK lecture or multidimensional rather, FSK and your multidimensional symboling or multidimensional constellations. Okay, so remember the case when we had infinite dimensions, your bit rate becomes a step function with negative 1.6 decibels as your at negative 1.6 decibels you get a step function. Anything greater than negative 1.6 decibels, you have a reliable communication system. Anything less than that, you'll always have a bit error. Okay, so this is another confirmation that the theory of Shannon is actually confirmed or is actually true. So to visualize that, this is your this is the graph of your channel capacity. So this is your theoretical channel capacity, the blue one, and the dashed red one is the Shannon limit. As you increase your bitrate, oh sorry, as you increase your bandwidth, you will approach the Shannon limit, as you can see right here. Basically, any uh, any signal to noise ratio less than negative 1.6 will guarantee or will not guarantee a good communication system. That's it. So this is the region where your bitrate is greater than the capacity, and this is when you won't be able to have a reliable communication system, right? So this region right here above is the bandwidth limited region, right? Region right here is the power limited region. Sorry, this should be swapped. Right? So this should be the power limited region because this is the region where you increase your spectral efficiency, and this should be the bandwidth limited region because this is the region where you increase your signal to noise ratio. Okay, so your different communication systems would be somewhere right here. Your ASK, sorry, your ASK, FSK is somewhere right here. Okay, all right, sorry, let me correct it again. This is correct. This is the bandwidth limited region, and this is the power limited region. I apologize for that, for the confusion. The bandwidth limited region is where your ASK, your QAM, your two-dimensional constellations gather. Okay, they're somewhere right here, and they have not even approached your Shannon or channel capacity limit near. Your power limited region is somewhere here. Okay, so the power limited region is when you don't have spectral efficiency but you have power efficiency. So your FSK is somewhere in this region. Okay. Again, they haven't even approached the channel capacity. So that's the state of our communication systems right now. We're trying to get near or nearer to the channel capacity that is postulated or that was derived by Shannon using his information theory. Anyway, so that's the state of our communication systems right now. All of our communication systems lie in this region. We have not yet achieved channel capacity ever. So that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting.